with Wireshark and Systemtap. My profession is with Red Hat. I'm a software maintenance engineer. My main duties are fixing bugs, fixing complex customer cases, helping other support engineers, learning new technologies. As part of my job, I'm doing stable release maintenance for GlusterFS. The GlusterFS 3.5 release is now stable, and I'm maintaining that branch. I am the sub-maintainer for the Gluster and NFS bits that are part of Gluster. So my name will be in lots of patches if you have any NFS issues or Gluster and network protocol issues. During my presentation, I would like you to ask questions as soon as possible. I've created this presentation as PDF, so I can easily switch between applications. You see the slide number in top. If you have a question about a particular slide or further on and refer to a slide, just remember the number and I'll jump back quickly. During this presentation, you will see a short overview of how Gluster works, because for debugging an application, you need to know a bit about the components, which components communicate with which other components. I will briefly introduce Wireshark, the abilities, what it can do, and how you can use it. I will show you an example of Systemtap, and Systemtap is an immense project. You can do many things with it. I'll keep it very simple and only use it for a certain use case to keep it in this 1 hour presentation. I've summarized 3 use cases or 3 problems that customers reported or users in the community reported. These include mount failures, which is relatively common, hanging of QEMU when accessing storage that is located on Gluster. QEMU is relatively new with Gluster integration, and some users have issues with that. There was also a very interesting case where the access time of modified files was not displayed correctly, and this causes all sorts of problems. Gluster consists out of many little components. The base component is called a brick. A brick is like a storage unit. If you have a RAID system, the brick would be one of the disks. Gluster is a network storage file system, and the bricks are located on different servers. You combine many bricks and you create a Gluster volume, so-called. All of these bricks contain several functionalities. A brick is a local file system. We advise you to use XFS, and this brick has many different layers of functionality. These layers are called translators. So, for example, accessing a local file system is done by the POSIX translator. If you would be so inclined to use a database to store your data, you can write a database translator, and you save all your files, all your metadata of the files in, for example, Postgres. There are caching translators, there are access permission translators. There is a translator for the network protocol, one on the server, one on the client. Everything is modular, and for each functionality, a single translator exists. The volumes in Gluster, as said, are combined out of many bricks. A brick is a local file system, just a directory on your server, and you combine many of these local file systems, XFS formatted, on many servers as one huge big volume. This volume is essentially the file system you mount on a client side. with Gluster, all the servers, we normally call them peers or storage servers, are hosting these file systems. The clients themselves don't need to do anything. Yeah. Any questions so far about how the basic Gluster infrastructure looks? As in the diagram, we have on the left side the mount point. You can see this as the client side. The distributed volume is one of the volumes that we support. It's a very simple volume to understand, and that's what I mostly use for testing. So we have two servers, and if you create a file, it will be located on one server or on the other server. You don't have any redundancy with a distributed only volume, but it keeps the complexity minimal. So for debugging, this is very useful. For production, it is not advised. You don't want to lose data in your production. So if you want to use Gluster in your production, you normally use a distributed replicated volume, which includes the additional functionality of copying files to multiple bricks. The client itself is running mostly on different systems. It is advised to split your storage servers and your clients that do have some workload, some batches on other systems. To understand how Gluster works, you need a bit detail on the protocol. So I summarized it very briefly here. When the client mounts, it contacts one of the storage servers. The storage server provides the client with a volume description, and this volume description contains all the host names and all the brick that each host hosts, and therefore the client knows which brick to contact for which file. This Fuse client ties into the Linux kernel through the Fuse kernel module on one side, and on the other side of the Fuse kernel module there is the virtual file system. So any user space process just uses the file system as normal. It mounts the Fuse file system. The virtual file system passes all requests on to the Fuse kernel module. The Fuse kernel module passes the requests on to a running binary, a daemon, and this daemon converts these Fuse requests into network traffic and passes this network traffic on to the brick processes running on your storage servers. The storage servers respond and the process goes backwards. In the diagram, to make it a little bit easier to understand, the Fuse client, also called native client, contacts all the bricks whenever it needs to do the application or does the distribution. There's no server in between that is a single point of failure. This utilizes the bandwidth of all the bricks, of all the storage servers, and you don't have bottlenecks this easily. There's also the possibility to use NFS or Samba to support CIFS clients like Windows clients or macOS clients. NFS is only supported in NFS version 3 at the moment. The NFS server is an implementation inside the Gluster packages. It is just like Fuse, one-layer translator. The top translator is either Fuse that ties into the Linux kernel with the Fuse module, or a translator that provides access through NFS. With Samba, we have another top translator, which is a GF API library, and we have a Samba module called VFS_GlusterFS, and this module uses the library and acts like Gluster client this way. So we have this access protocols. If you compare that to the previous views, the NFS server is running the Gluster client, and the NFS server will contact all of the bricks. With the libgf API, which is just another client, you can tie it into Samba, you can tie it into QEMU, or any application you like, and this client will access all of the bricks, it will speak the GlusterFS network protocol to the bricks through the libgf API library. Who knows Wireshark? Okay, so if you used Wireshark before, you might know what kind of details you can gather from a network capture. If, for example, if you use Telnet, you should not use Telnet, but if you use Telnet, you would be able to see the login names and the passwords in plain text if you capture the network traffic. And this is an easy way to show the abilities of Wireshark. You can capture network traffic, you can see anything. Telnet is a very simple protocol, so you can easily see the contents. If you see the protocol of, for example, a virtual machine doing storage on network file system, you would see the network file system protocol, but the contents of the image, what it is doing, if it's creating files or reading files or writing files, will be very unclear because it is encapsulated in a big binary blob. With version 1.8, we now support GlusterFS. That was my first experience with adding support for Wireshark, because when Red Hat bought Gluster, I was one of the engineers that was supposed to learn about Gluster and support customer problems with that. The first thing as a support engineer is, or what you do, is to capture network traffic and see, okay, we have a network file system, so how does it compare to NFS? What details can we get? If you capture this network traffic with previous versions, you would see only communication going back and forth, and you will not be able to see any of the details. With newer versions of Wireshark, there's the implementation of the Gluster protocol, and Wireshark now knows which procedures are executed, which sub-protocols of Gluster are used, and it can display all possible details, like file names, the contents of the files, what is happening. So it's very, very useful now, and we use it in support quite a bit. Other useful command line tools are T-Shark. It is a console client for Wireshark. It makes it much easier to copy-paste, for example, output of Wireshark captures into emails or support cases in my case. With Wireshark, the graphical implementation, you would need to make screenshots or something similar, and that is very painful to share with others. Capturing is easy done with Wireshark itself. You start the graphical application, you click on the buttons and say, okay, I want to capture this network traffic. The thing is that if you capture this network traffic that way, you would need a graphical interface on your server, which hopefully very few people have. The best way to capture a network traffic on a server is using TCP-dump. It is very basic, it doesn't do a lot of analysis, but it can capture big files, it can capture all the details, and you can copy your TCP-dump capture in a file afterwards to a workstation and debug it there, or you open a support case with Red Hat, and the Red Hat engineers will look into this. An example for capturing with TCP-dump, you give it a file name with -w for writing. You capture it on interface depending on where you want to capture and how your interfaces look like. You can use -i any to capture on any network interface. So if you are on, for example, a gateway or a router, you would capture on the incoming and on the outgoing interfaces, and you will have all the data. This is very useful, for example, for the NFS server in Gluster. You will capture the NFS protocol on the incoming side and the GlusterFS protocol on the outgoing side, because the NFS server is just something like a gateway or proxy. For a lot of things, you do want the whole contents of the packets. The packets are normally trimmed to 512 bytes, I think, and setting the size to 0 will make it possible to capture all of the packets. This is needed, for example, if you do a directory listing. A directory listing contains a lot of metadata for files, and without this metadata, it will be very difficult to follow what is going on in the TCP dump. So you need all the metadata, you need to be able to get all the details, and 512 bytes just isn't enough for that. Fortunately, Wireshark is only TCP, and the ports are quite well defined. The full command that you can execute is on the bottom list. Any questions? I actually have a giveaway today, too. So if you ask good questions, you can win either a t-shirt or a Red Hat voucher for training. So think about questions. I really would like to hear them. And me and my support engineers can vote which question is the best and who should deserve these vouchers. A little bit about the Gluster protocol. The Gluster protocol itself is completely undocumented, which makes it very difficult for support engineers to understand the protocol. Fortunately, reading the source code is possible because we all do open source, and the Wireshark support for Gluster was completely reverse engineered from the sources. The underlying protocol, just like TCP and IP, there is a RPC protocol. It's called SunRPC, and this protocol fortunately has an RFC and is completely documented. It is more or less like the header for the Gluster protocol. This header and the Gluster protocol itself is encoded in XDR. You could also encode such protocols, for example, in XML, which is relatively new. XDR is a very old standard, and it's used for NFS and other similar protocols. So the Gluster developers decided to use XDR, and we're very happy with that they don't use NFS or JSON for it. Gluster itself uses many different protocols. There's a protocol for managing storage servers. There's a protocol to do file I/O. There's a protocol to talk from the command line interface to the management daemon, and so forth. There are many protocols, but the GlusterFS protocol that does the actual I/O is mostly the most interesting. It is used by the Fuse client because the Fuse client talks directly to the bricks, just like any client, and you would be able to see most details you want to need, unless you want to debug mount issues, because mounting is done initially over a different protocol. Systemtap, this comes from sourceware.org, and Red Hat is one of the major contributors for this. It is used to mainly debug kernel issues. You write a small script, or if you want a complex script, and you can debug or print or count accesses to functions. You can print variables inside functions in the kernel itself, which is very interesting for support engineers. And if you want to debug really difficult things, Systemtap is at least my choice as a tool. You can use it for user space. If you use it for user space, you can compare it with GDB. A lot of developers know GDB and go through their program, and they step through the functions, which is possible if you have a program and you know more or less the area where you want to look. This is not so useful for Gluster. Gluster is very multi-threaded, and there are a lot of interactions. So you really have to be one of the main developers for such a component to be able to understand how to use GDB. Systemtap in that case is much easier because you can just see everything that you need and you filter that afterwards. It's also an option to pass Systemtap modules onto customers, for example. A customer does not know GDB, and instructing a customer how to use GDB is extremely complex, especially if it's just written or over the phone. Giving them a Systemtap script is an easier solution. You tell them to run the Systemtap script, wait until the problem happens again. They stop the Systemtap script, and you have all the debugging data that you actually need. Systemtap scripts get compiled as a kernel module and loaded into the kernel and unloaded when the script is done. The documentation for Systemtap is very good. It's very helpful. It's normally located on your local file system when you have it installed. And there are many examples, many available functions that make it easier to work with. Any questions so far on the tools or on how Gluster interacts? Yeah? Yes.
Okay.
Yeah.
Introduce the lib that any application can connect and have access directly to the GlusterFS, right? My question is, instead of mounting it in another server, I can access through this lib the Gluster. My question is, can I have, let's say, an Apache server, an HTTP Apache server that's connecting to this lib and accessing Gluster instead of mounting it in the Apache server? And in this case, it has a better performance than mounting it?
Yes, yes. So that is why the library was written and provided. We mainly use it, or the first real usage is in Samba and in QEMU. In QEMU, we had IBM developers that were requesting for this functionality because before QEMU integrated this library, they would mount the file system over views and store their image files on this views file system, which has a lot of performance impact. Every time you want to use the files on the views file system, you have a lot of context switches. I think I don't have the slide here in this presentation. I have it somewhere on my laptop, but we have a presentation that contains how many context switches are done to achieve access, for example, for a read or a write. I think it was something like, I don't know, 32. Let's say 32. But something in that area. And context switches really hurt performance, especially if you do an ls in your directory and you have to, after that, you will check every file again. So you do ls, that causes 32 context switches if the directory listing is not too big. And for every file in that directory, you will ask some more data. You do a stat on the file, or you want to know what the contents of the file, the size, or whatever. And this causes more and more context switches. So this is it's a big performance hit. With this library, you do not mount the file system. You don't have all these context switches with the views module, because if you access a file through the views module, you have to go through the file system, through the kernel, through the views module, and then the views daemon that runs in user space again. With this library, you run completely in user space, and only the network access needs context switches, because network access is handled by the kernel. So the performance is much better, and you can write a, for example, an Apache module that supports mounting the views volume, or mounting the Gluster volume, and without mounting it in the file system itself. So yeah, one of my side projects I've started is indeed writing such a module for Apache. I have not been able to do performance tests yet. It's an initial trial, and hopefully in the future I'll be able to find some time and compare performance of a plain website, because static contents is what we target with Gluster, or mostly target, and yeah, hopefully the performance is much better that way. So that is exactly how Samba does it, how QEMU does it. The IBM team that wrote these QEMU additions, they have over 200 performance improvement, over 200% performance improvement. So yeah, they are very happy with this library, and they are the main guys that want more functionality as QEMU supports more functionality, and yeah, so that is very good. Any other questions? No? So one of the common issues that community members mostly have is that mounting fails. Mounting of the cluster volume fails for whatever reason. So these are the steps that I would take to see why such a mount process fails. It contains a little bit of detail. So the easiest filter to filter any of the standard TCP stuff is checking for the length of a package. The contents of the TCP packet should be bigger than 0. If it's 0, then it's just TCP communication, setting up the connection, and so on. That's often not very interesting for Gluster. So some of the protocols, Gluster Handshake, Gluster Dump, Gluster Port Map, are done before the Fuse client actually contacts the bricks. So after the Gluster client receives the reply from the port by brick procedure, it knows for which brick, for which host, which port is used. So it knows which port to connect to and which server it is. It should connect to the bricks, and often it just fails there. So what you would do is you would check the reply packet and check if you can find where the issue is. So let's see. So I have a standard filter. I think everyone should be able to read this. Is it big enough? Yeah. So standard filter, you would say, okay, I want to have the length, or only packets with the length bigger than 0. Otherwise, you would see a lot of stuff. This is marked as TCP, and these are interesting packets. So this is much better. The conversation is much smaller, and we can actually see what it's doing. So going back to the presentation, I said, okay, we want the Gluster Handshake. We want to see what gets back. So this is a call. This is an RPC call. It says over here. It is a call. It is a GlusterFS handshake protocol. The procedure is a gets back. It contains credentials like the process ID and whatever is done. The procedure is the get spec, so get the specifications of the volume, which means give me the volume definition file, give me the layout. The key is the name of the volume, and it provides which versions it supports of the protocols. Now this is the call, and we would like to see the reply. Wireshark is very intelligent on this base. It knows which packet contains the reply. So double click on the packet, and it jumps to the reply, as here in the header or also here. The square brackets between for these attributes are generated by Wireshark. Wireshark knows it is a reply, and in the RPC procedure call, the procedure and the program number and everything was listed. So Wireshark just caches it and says, okay, remember this was a Gluster handshake and this is the reply on the get spec call. The return value is, in this case, the size of the volume definition file. And success, no error. Wireshark truncates the contents, which is okay, we can show it anyway. So this is the raw TCP stream, and this is the volume file that the client receives. To compare, you can even see it here. So this is the volume file, the volume definition file that contains how the client should structure its translator list. This file is the same content as that was received here. So the Gluster storage server reads that file, passes it on to the client. Okay, so we've done the get spec. That seemed to have worked quite fine. The next is Gluster dump. Gluster dump is a protocol to check the functionality of which brick supports which versions and so on. So a Gluster dump call, there's a reply, there's more calls. It does that for every brick because it receives the volume layout, so it knows which bricks exist and on which system or which host they are running. So I can give you a short show. It says, okay, I want this ID, and babe is the request for, okay, give me all the functionality you have or which programs you have, and the reply is something like this. So we have a RPC program, Gluster dump, we have an RPC program, Gluster D. These are all the sub-protocols that Gluster has, or that this storage server supports. And okay. Yep, so in this case we have all these dumps. If you go through them, they all have a call and a reply. That's good. So after that we do a port map. Gluster includes a port mapper similar to RPC bind or port map used for NFS. Port map registers a service, and users can ask for the service, and this port mapper says, okay, the service is listening on port XYZ. So the service doesn't always need to listen on the same port. HTTP always listens on port 80. Otherwise, clients would not know how to interact with it. For Gluster, the ports are assigned dynamically, and only the port mapper is listening on a well-known port. So clients contact the port mapper, and these clients request the actual ports used from the port mapper. So in this case, the client asks, okay, I want this brick. Yeah. Which port are you listening on? And if you compare the reply, the port by brick command returned success, and the port is 49,155. That's the port range the bricks normally listen on. So that's all good. Now, after that, it should connect to each brick. However, we don't have any captures here anymore. There's no packets listed. But we did have a filter. So clearing the filter shows, okay, this was the last port by brick call. Now we have some TCP connection. So it tries to connect on this port, the 49,155. And the brick responds destination unreachable. So now we have seen that the client does almost all the mount process, or all the procedures done for mounting, but only the last bit, the connecting to the port, failed for whatever reason. In this case, I simulated to show you with the ICMP reply a firewall. There's a firewall on the storage servers, and the client is only allowed to connect to the known port and not allowed to connect to any of the other ports. So any access to bricks will fail, but connecting to the main port, the port mapper that does the rest of the procedures to prepare for mounting, that worked perfectly fine. With the reject rule in IP tables, you will generate an ICMP destination unreachable. If you use a drop statement instead, it would just absorb the packet and would not send any replies. So those are a bit trickier to define or to diagnose. So sometimes you have to capture a TCP dump on both the client and the server, sometimes even on systems somewhere in between the whole communication path. Sometimes there are routers or firewalls between, or completely separate firewalls and routers, appliances between the Gluster storage and the client, and they can drop packets or similar things. That was the first use case. Any questions on how this works or how this can happen? Yep. Sorry. Can you give the mic?
Hi.
Yeah.
During the mount handshake.
So sorry, a bit.
Okay. Can you hear me now? During the mount handshake, you receive the hosts for the bricks, right?
Yes.
That you are connecting. Is there any algorithm on the server side that I can return based on the my client latents, for instance, like depending on where they are, I can return different replicas for the files?
Not yet. So there is for the next release or the release after that, if we don't make it, there is a sub-project started to start data classification, and that is supposed to become, for example, rack aware, so that you can assign data to racks, and your clients located close to that rack would be able to have higher or better performance than in other racks. But at the moment it's not there, and the client will just connect to all of the bricks. It doesn't care where they are. Yep. You guys remember the question and judge it afterwards? You have to pay attention now. Okay. No more questions? Yep.
Hello.
Yeah.
On a replicated brick, maybe radio 1.
Yeah.
Will the mount fail if one brick is not reachable?
So depends on how your setup is done. You will indeed give one storage server, or when you mount, you pass normally one storage server. If during mount time that storage server is down, you will not be able to reach it, and this storage server will not be able to give you the volume file, so the client does not know which other servers are available. You can pass as mount parameters a backup storage server, or multiple even, and if the first one fails, it would try the next one and the next one and the next one. That is one solution. The other solution is to use failover IP addresses or floating IP addresses. If you use, for example, CIFS or Samba, then most users will have floating IP addresses or virtual IP addresses anyway, and they will those IP addresses will be used for mounting mostly. So those are the two common solutions for this. It should solve any issues. Yeah.
I have another question, but it's not so related to debugging. I don't know if you want me to ask now or at the end of the.
It depends on your question.
We are currently using a small setup of Gluster for testing purpose.
Yep.
And thinking beyond that, in creating a large environment, I was thinking if you believe that's possible to create an infrastructure that using RAID and multiple servers, if you can achieve a very high reliability of this setup, maybe I don't know 90%. If you kind of reliability, you can think of not having a backup of those files.
Well, backups are always advised, and especially if you run in one data center, you still want backups. You have no idea what could happen to the data center. So for that, there is an offsite replication mechanism for disaster recovery. It's called geo-replication, and that would be one of the solutions to use. So you use geo-replication. We have customers that have their local data centers with Gluster running, and they use geo-replication to store the contents, the backups, the automated backups, either in Amazon Cloud or on remote data centers somewhere on the other side of the world. So the availability is there, and that is exactly why geo-replication exists. It makes sure that even if your whole data center catches fire, you still have a backup somewhere else, because backing up huge storage is one of the difficult things to do here. Yep. Okay. Anything else? Then I'll go on to the next issue. So I mentioned that QEMU now has support for direct accessing Gluster, and this is done through the library. With this new support, configuration is a bit trickier because things have changed. So there are sometimes issues if you create an image. If you create, for example, with QEMU image, if you create a new file, the error message is a bit, the screenshot is a bit small. It's part of the log that Gluster spits out on the error. The most important part in this is that the set volume procedure fails. Set volume fails, and it says remote host failed, authentication failed. Even though mounting the Gluster volume is no problem at all, it works very fine. This is an issue that happens with creating QEMU images. It also happens if you want to start a virtual machine. So if you copy the image over the Fuse mount and you want to start this image through QEMU with the libgf API integration, you can run into this problem. So I start off with the same filter, checking for the length of the packets, and you see that it very much resembles the mounting. So there's the handshake, there's the dump, there's the port map, there's the dump. And then something we did not see before is the GlusterFS handshake. It connects to the bricks and does the set volume call. In this case, the set volume call fails, as the logs showed. So this is the call. And okay, it passes some information on. It says, okay, we have this log version, we have the name of the volume, the version of the client itself, the process, so that you can identify exactly which process it is. If you have multiple QEMU processes running, for example, they would all have a different PID, and the PID of the process ID is 1447 in this case. Okay, so some further data, and this is what it tries to attach to. So set procedure failed, or set volume procedure failed, and the reply says, okay, we have a return value of -1, and we get a permission denied. Okay, and further details in the protocol says, okay, we have authentication failed. This is what also was listing here. And the process actually hangs in this case. So if you start, or if you want to create an image, the process will hang after a while. It takes a couple of seconds. With starting a virtual machine, you don't notice it immediately, because starting a virtual machine always takes a little time. Creating an image is an easier way of checking. So in this case, after some debugging and checking the logs and things, it is seen that the bricks return permission denied, and the configuration guide to allow any process to connect to the cluster volumes, because normally only privileged processes with privileged port numbers are allowed to contact. QEMU and creating an image does not use privileged ports for the GlusterFS library. You normally don't execute them as root. So you need to set additional options to the volumes and the Gluster servers. If you follow the procedures, you're perfectly fine. If you follow the procedures badly or partially, then you run into weird hangs. And you won't be the first, because I've hit this particular issue myself too. You want to start a virtual machine, and suddenly this virtual machine just not do anything anymore. It doesn't even start. It doesn't even show the BIOS when it starts. So something is awkward. And instead, so the documentation says, okay, you have to stop and start the volume, which is not the same as rebooting your cluster servers. Stopping and starting the volume triggers a regeneration of the volume definition files for the bricks. The bricks contain a very similar file as what the Fuse client receives. The bricks receive a very similar file, and it contains options, for example, permissions. And it says, okay, you're allowed to connect from insecure ports, ports higher than 1024. If this option is not set, the set volume call will return an error and will fail. So this hang, a virtual machine hang, is really annoying. Really can be really high urgency or anything. But if you follow the documentation, you should be able to figure it out and go through the steps again and find, okay, I forgot to stop and start the volume. So it takes a little off time. There should be patches that it's done dynamically. I'm not sure how far the patches are currently been reviewed. That's one of the things that I hope to include in the next 3.5 release for Gluster. Any questions about QEMU? Then I'll just skip to the short Systemtap example. So the problem is that, or was, that writing to a file on a Gluster volume, the access time would be way into future. At least on Linux. On Windows, in Explorer, it would have an empty field if you see the properties of the file. There would be no access time at all. Not even 0. It would be empty. It would not be listed. debugging this is how the access protocol looks like. So you have the CIFS client, the Windows workstation or Linux workstation mounting the Samba share, Samba with libgf API integration, and then below that is the Gluster storage servers. To check the connection on this part, the Samba part, what Samba receives from the client. Oh. We wrote a Systemtap probe that uses this Samba module or hooks into this Samba module and actually wants the details in this Samba function. This is a function inside this shared library, the plugin that Samba uses, and you can use printf to print the function name and the time. This is the parameter that is passed to the function. You have to check the source code to know the names of the parameter. And okay, the parameter is a structure. The structure contains access time, and the access time contains seconds. The same for the modification time. The resulting output was something like this. You can see that Gluster, the function that we just tracing, so this function returns -1 or has a time of -1, which is very awkward. This function inside the API passes this on immediately. So where is the issue now? We receive this from the CIFS client and we pass it on immediately to the storage servers. Reading some more source code, mainly of the Linux kernel CIFS client, it seems that -1 is a special defined for access time in CIFS, and CIFS sets -1, and it's actually called no change. So it's a you should not pass this no change access time. You should not set that on the brick servers. You should not pass it on to the storage servers. Unfortunately, libgf API requires you to send the access time and the modification time in one procedure call. It is based on POSIX procedure calls or functions, and this is a requirement. Fortunately, Samba caches this access time internally. So what you do is you just copy the access time that Samba has cached in case the access time was -1, and you pass that on. So this is a patch that I've written for the upstream Samba project, and after a review and some modifications, the guys accepted it, and it's now part of Samba, part of Red Hat storage, and part of any current deployments. A link to the patch and a discussion. That's it. I don't have any time to answer more questions, but I will be outside. If you have questions, come to me. Meet me and these 3 guys as judges. I will make these slides available on my Red Hat people page. So my name is Niels de Vos, and de Vos /talks, Fisl 15. Thank you very much.